All right, today we're going to learn about something called implicit differentiation. And to start out, just so we can talk about that, I want to talk about first what we've been doing so far. So basically, every derivative that we've taken so far in this class, the equation has been written in what I like to call y equals form. And the actual name for that, it's called explicit form. So what we've been doing is we've been doing explicit differentiation, meaning we've been taking the derivative explicitly. And today we're going to learn how to do it implicitly, which is a little bit different. So in explicit form, which is, like I said, when I usually call it y equals form, basically what you have is on one side of the equation, you have either y equals or f of x equals or g of x equals. It's basically the function itself equals. And then on the other side, you have an expression with x's only. Now, if either of those two things changes, then we have to use what's called implicit differentiation. So what that means is maybe over here on this side, you have something other than just y equals. Maybe you have y to the fifth equal, or maybe you have y plus 10 equals, or anything other than just y on this side. Or on the other side, if you have anything other than just x's, if you have some y's mixed in there, or maybe there's a third variable, some z's in there, that's when you use implicit differentiation. So an equation in any other form, anything other than just y equals on one side, or f of x equals, and just x's on the other side, then it's called implicit. So here are some examples of implicit equations. Like I said, for the very first one, maybe instead of y equals, it's y squared equals. You could do implicit differentiation. Or maybe you have everything all jumbled up, x squared plus xy plus y squared plus 10 equals 0. That's definitely an implicit differentiation question. Or right here, this is a real common one. If you ever have an x and a y like combined like that, that's a very common implicit differentiation question. So those are the ones that we're going to learn implicit differentiation, so we can take the derivative of those equations also. All right, so let's start off with this notation I used with you guys earlier. Way back when I first taught you derivatives, I said there's a couple different ways. You can use the apostrophe. You can say y prime or f prime of x for derivatives. But I also said there's this other one, this dy dx, dy over dx, that we just say dy dx. That's the derivative, and today is when it's going to become more important that we really understand that notation. So what it means, the top tells you what you're taking the derivative of y, and the bottom tells you what you're taking the derivative with respect to. And that phrase right there, as we move on through the rest of chapter 4, and we talk about both rates and related rates, that phrase with respect to is going to become very, very important. Now for right now, we're going to only differentiate with respect to x, but soon we'll be changing that and taking the derivative with respect to other letters. So here's how it works. Whatever you're taking the derivative with respect to, just do it normally. Like the derivative, if you're taking the derivative with respect to x, the derivative of x to the 5th power, you just do power rule. It's 5x to the 4th, or anything at all. But remember, what makes this an implicit equation is that there are other variables mixed in, probably y's for us, but it could be anything. So any other variable, if I'm taking the derivative with respect to x, and there's y's or z's or p's or q's or anything else in the equation, then you have to take those derivatives a little bit differently. So let's talk about how we're going to do that. So what I have here, I'm going to go through some derivatives of x versus other variables with respect to x, and then you can see the difference. So here's the one I mentioned earlier. I mentioned in the last slide. I said the derivative of x to the 5th power, that's an easy one. It's power rule. You multiply by 5, you lower the exponent by 1, you get 5x to the 4th. That's a normal derivative. And what you notice, remember this is another notation I've been using. This d dx right here, what I told you earlier is it means just take the derivative. What it actually means is take the derivative with respect to x. So the derivative with respect to x of x to the 5th is just 5x to the 4th. Now let's say I want to do the derivative of y to the fifth with respect to x. Now I already put the answer on there, but let me show you where it comes from. This one right here looks exactly like this one right here, but with a y instead of an x. And that's what you do. You take the derivative of that y function normally first. But then what you're actually going to do, what it technically is chain rule. So remember when we said for chain rule, any derivative that you know how to do for x, if you take the derivative of something else, you have to multiply by its derivative. So that's what we're doing here. We're saying I'm taking the derivative of something else to the fifth power. So I do the power rule, I get 5y to the fourth, but then I have to multiply by the derivative of y. Well, the derivative of y with respect to x is dy dx, and that's where that comes from. So there's kind of a shortcut way of thinking about this. And just to show you it works with any letter, if I did the derivative of p to the fifth power, I take the derivative, I get 5p to the fourth, and then I multiply by the derivative of p, which is dp dx. So you can, we're going to focus mostly on x and y for right now, but you can put any letter you want in there and it'll work. All right. So here's that little shortcut I was telling you guys about. First of all, I said this is basically the chain rule. I explained that on the last slide. You're taking the derivative of something other than x. You do the derivative that you know how to do anyways. In that case, it was power rule. And then you multiply by the derivative of whatever that letter is. Here's the shortcut. For implicit differentiation, think of it as two steps. Any x term, just take the derivative of normally. You don't even have to think of it as an implicit differentiation question. Take the derivative like we've been doing for about a month now. Power rule, product rule, chain rule, quotient rule, whatever you need to do. Now, for any y term, take the derivative normally, and then just stick a dy dx on the end. I mean, the chain rule is always going to be the same thing. So instead of thinking of it as chain rule, you can just think, yeah, I'm just going to take the derivative of this y term, and I'm going to stick a dy dx on the end of it. All right, so when it comes to the actual process of an implicit differentiation question, here's how it's going to work. Step one, you differentiate both sides of the equation. And that's what's different about this type of problem. Every derivative we've done so far, it's y equals, but we don't even think about the y equals or the f of x equals. We only differentiate one side of the equation. Now all of a sudden we're taking the derivative of both sides of the equation. Now, usually in this type of question, you're going to end up with more than one dy dx in your answer, and that's what you're trying to solve for. You're trying to find dy dx. So what you got to do is group them together so you can factor them out. That's the way, if you have two or more of something in a problem and you want to turn it into one of something, that's the way you do it. You group them together and factor it out. So what you need to do is get all your dy dx terms together on one side, get everything else on the other side. And I said left and right on the slide. It actually doesn't matter which side. Then what you do is you factor out the dy dx. You basically divide both sides by what's left over, and that'll be your answer. Now, it sounds pretty complicated, but once you've done a few of them, it becomes more comfortable. So let's do a couple together now. Let's start with this one. We're going to find dy dx, meaning find the derivative of y with respect to x, of y plus 5 equals y squared minus 2x. Now, when I first look at this question, I know it's implicit differentiation because, number one, it's not in y equals form. Although I could very easily get this in y equals form. If I just subtracted 5 from both sides, it would say y equals y squared minus 2x minus 5. But I'm not going to do that because it still would need implicit differentiation. The main reason I need implicit differentiation on this question is because I have a y here and a y squared there. If you have two or more y's in the same problem, you're almost certainly going to have to do implicit. All right, so once we've decided that we're going to take the derivative implicitly, I'm going to go through and I'm going to take the derivative of both, or I'm basically going to take the derivative of every part of this equation. So let's do that. Let's start with the first term, the y. The derivative of y with respect to x, and remember what right here, that tells you what you're differentiating with respect to. So for this whole question, I'm taking the derivative with respect to x. So first of all, the derivative of y with respect to x is just dy dx. So I get a dy dx for the first part. Okay, we move to the next term. The derivative of 5 is 0. Remember, it doesn't matter how you're taking the derivative, explicitly or implicitly, the derivative of any constant is always 0. Okay, so now we get the derivative of y squared. So what I'm going to do is I'm going to do the power rule. I'm going to multiply it by 2, lower the power by 1, so I get 2y, or 2y to the first power. But then remember, I get a dy dx there. And you can think of it as chain rule, or you can just remember every time I take the derivative of a y term, I stick a dy dx on the end. And then we get to our last term, negative 2x. Now this one is an x term, so I'm just going to take the derivative normally. The derivative of negative 2x is just negative 2. All right, so if I clean this up a little bit, there's not much I can do. I can get rid of the 0. dy dx equals 2y dy dx minus 2. So now what you want to do, we've taken the derivative implicitly, but we haven't answered the question. The answer to the question needs to say dy dx equals something. And this is the part where I notice I have two dy dx's. I have one here, and I have one here. If I want to solve for dy dx, I can't leave them separate. And this is where I was saying you need to group them together so you can factor it out. So let's do this. Let's just subtract 2y dy dx from both sides of the equation. Basically just to move one of the dy dx terms over with the other. We're going to cancel out that whole term right there. So what I get is my original dy dx minus 2y dy dx, and it's all just equal to negative 2 now. Now the whole reason I did that is because now, if I I'll put some parentheses on here, I can factor the dy dx out of there. So I'm basically going to divide dy dx out of there. Now that first term, if you have a dy dx and you factor it out, it leaves a 1. So remember, if you ever have something and you factor the entire thing out, it doesn't just disappear. It doesn't leave a 0, it leaves a 1. On the second piece, it leaves 2y. I factored out the dy dx, it leaves the 2y. It's still equal to negative 2. And see now, I've basically fixed that second problem I had. Instead of having two dy dx's in my problem, by factoring it out, I now only have 1. And I can finish with one more step. You basically just have to divide both sides by whatever was in the parentheses, because that'll cancel. And your answer is negative 2 over 1 minus 2y. So that's implicit differentiation. The first step was what I did in yellow. That was just the derivative, taking the derivative implicitly. That's our brand new thing for today. The second step, the work I did in green, that's where you have to make yourself able to solve for dy dx. If you have more than one of them, you group them all together and factor it out. And then in blue was the work where I did that. I factored it out and I solved. All right, let's take a look at one more example just to make sure you guys got this. Same setup, we're going to find dy dx again. And I have that same kind of setup where I have two different y. This one actually is in y equals form. But the fact that I have that extra x over here, it's not a function of x. So it is in y equals form, but it's not y as a function of x. It has both x's and y's in it, which makes it an implicit equation, and we have to use implicit differentiation. So let's go ahead and do that. So I'm going to take the derivative of each part again. Let's start with the y. The derivative of y is dy dx again. Now, what we have, this xy, that's a product. xy means x times y. So when we're doing the derivative, you have to do product rule. Derivative of the first times the second plus derivative of the second times the first. And what I'm doing is this one right here, this product, x times y. So be careful on that because you're going to see product rule and chain rule and quotient rule all mixed into this. So let's see, derivative of the first. Derivative of x is just 1. Remember, we take the derivative of x terms normally, times the second, which is y, plus the derivative of the second. Now the derivative of y is dy dx, times the first function, which is x. So that's my product rule right there. Derivative of the first times second plus derivative of the second times first. Now we still have one more piece to this equation. The derivative of 5x, that's a nice easy one, it's just 5. Because we're taking the derivative of our x terms normally. So let's see what we have here. We end up with dy dx equals y plus x dy dx plus 5. And now we're at the same spot we were in the first example. I have two dy dx's. I have one here and one here. So let's group those two terms together. Let's basically take this term right here and subtract it from both sides. Subtract x dy dx from both sides. Cancel that one out. And we get dy dx minus x dy dx equals y plus 5. And then this question is going to end. In fact, what you'll notice as you're doing this work, you guys, is these questions end very similarly. Once you get that work done in yellow, the work starts to feel very familiar. Okay, group the dy dx's, factor it out, divide, get your answer. So these questions do seem very similar. They will get familiar for you guys. But we'll factor out the dy dx. It'll leave me this time 1 minus x, because I get a 1 from the first piece and an x from the second. And it's all equal to y plus 5. And then we'll divide both sides by 1 minus x to cancel that. And that's the answer, that's dy dx. So for my final answer this time, I get y plus 5 over 1 minus x. And one thing I want to mention here before we wrap things up, you'll notice, and this is very common, in your answer over here, you have both y's and x's. So your answer is also an implicit equation. When you do implicit differentiation, your answer is an implicit equation. So you can definitely have both x's and y's in your answer, but you don't ever want to have a dy dx in your answer. So like a lot of times people will give me an answer like this. They'll basically like box this one up right here and say, well, that's dy dx. It says dy dx equals. Well, you can't have a derivative in your formula for a derivative. That's why you need to group those and factor them first. All right, we're basically done, but there is one interesting thing about this example I want to show you guys real quick. So let's take another look at the same problem. Unlike the first question, this one you actually could have solved without using implicit differentiation. So let me show you how that would work. I'm not going to work out the whole thing, but I'll start it for you guys. Let's say instead of doing implicit differentiation, right at the beginning, I had subtracted xy from both sides to move that term. So you get y minus xy equals 5x. Then you factor out the y. Y times 1 minus x equals 5x. Then you divide by 1 minus x. So you're doing the work we usually do at the end, at the beginning. So what you get is y equals 5x minus 1 over x. This is now an explicit equation. And you could do this normally. You could do this without implicit at all. You could do it, it would be a quotient rule question. It would be derivative of the top times bottom minus derivative of the bottom times top, all over the bottom function squared. And that's the part I'm not going to do because that's not really what we're working on right now. But I just wanted to show you certain questions can be done that way. Our first question could not be done that way because one of them was a y and one of them was a y squared, and you can't factor that out. So just something for you guys to think about. I always like to point out when there's more than one way to do a question because it's good for you guys to start thinking about that.